A sleigh and its occupants have a total mass 500 kilograms. The coefficient of friction between the sleigh and the snowy ground is 0.1. If a husky dog can pull with a horizontal force of 100 newtons, find the limiting friction. Let's suppose that no husky dog is pulling on the sleigh, so the sleigh is sitting here at rest, which means that its acceleration is 0. Let's look at the forces acting on this sleigh. Well, we have the weight of the sleigh, which is vertically downwards. Its magnitude is the mass of the sleigh and its occupants, which is 500 kilograms, times the acceleration due to Earth's gravity, g. Now, by Newton's second law, if the acceleration is 0, it means that the resultant force on the sleigh must be 0, because the resultant force is given by mass times acceleration, and mass times 0 is 0. So this can't be the only force acting on the sleigh. We must have another force acting on the sleigh, such that when we add it to this force we get 0. That other force must be pointing in the opposite direction, but with the same magnitude. So I will call this force N. Its magnitude is also 500 g. So the resultant force F is the vector sum of these two forces. So I'll just write down this vector equation. So we've vector N plus vector W is 0. So the sum of these two vectors is 0. And that's always the case, even as the sleigh is moving horizontally. So the acceleration will not have a vertical component. The acceleration will be entirely in the horizontal direction. That means that the resultant force on the sleigh will not have a vertical component. The resultant force will be entirely in the horizontal direction. Now, in some texts you might see this force called R. Now R looks like this force is a reaction to this force here, and that's certainly not the case. So it's a bad idea to call this R, because it looks like we have an action-reaction pair here. Now, I've explained in previous videos that this pair comes about from Newton's second law, not Newton's third law. So I won't explain that again. So it's better to call this force N. N is the force on the sleigh due to it being in contact with the horizontal ground. N is a contact force. It has a different nature to W, which is a gravitational force. N means normal. Normal means the force is perpendicular to the surface of contact. Now suppose that we have a horizontal force acting on the sleigh. Let's suppose it's acting to the right. Let's call this force P, so the magnitude is P. Well, let's suppose that that force P starts off at 0 and keeps on increasing. Now, unless the surfaces are perfectly smooth, the sleigh will not begin to accelerate until P reaches some maximum value. So there is a force resisting the motion of this sleigh. That force is in a direction opposite to the subsequent motion of the sleigh. So the direction of that resistance force is to the left, and this resistance force is called the force of friction. So that comes about because the surfaces interleave to some extent, unless they're perfectly smooth. So as P increases, the friction force, which I will call small f, keeps on increasing in magnitude until it reaches some limiting value, and that limiting value is called the limiting friction. Once the friction force reaches that limiting value, the sleigh will begin to move to the right, and if P gets bigger than little f, then the sleigh will keep on accelerating to the right, but the limiting friction will keep on acting to the left. So whatever the limiting friction is, it'll remain constant once P gets to be greater than F. Now, from experiment, the limiting friction depends on the normal force and also the materials of the surfaces in contact. F is given by mu times n, as I've explained before. Now, in this situation, the coefficient of friction mu between the sleigh and the snowy ground is 0.1. And we can see that n is 500 g. So this works out to be 50 g newtons, that's 50.9.81. Well, that's approximately 490 newtons. This N stands for newtons, of course. Don't confuse it with N over here, which stands for the magnitude of the normal force. So this means that for the sleigh to start moving, the pulling force P has to have a magnitude of at least 490 newtons. So the magnitude has to be greater than 490 newtons. Then the sleigh will move to the right, and a friction force of 490 newtons will act continuously on the sleigh. So we'll have a constant force of 490 newtons in magnitude acting to the left. So no matter how big P gets, this constant force will be acting to the left. This force will never change, even as P increases, as we increase, say, the number of dogs that are pulling on the sleigh. So in part 2 we want the least number of dogs needed to get the sleigh going across horizontal ground. So each husky dog can pull with a horizontal force of 100 newtons. So how many 100 newtons fit into 490 newtons? So we just have 490 divided by 100. So that's 4.9 dogs. We need at least 4.9 dogs. Of course we can't have 0.9 of a dog, so we need at least 5 dogs. So 5 dogs is the answer to part 2. So we could imagine for each dog we have a vector whose horizontal component has magnitude 100 newtons. Of course the dogs don't all have to be pulling in the horizontal direction. Dogs could be pulling in directions that are not entirely to the right, if you know what I mean. But the idea is that the component of those forces pointing to the right will have magnitude 100 newtons. So we will have 5 of them. And to sum these components, we just add the magnitudes because these are vectors pointing in the same direction. So it's easy to sum each of these. So each of these is 100 newtons. So here's the resultant of those horizontal components. So P will be 500, and of course F is always 490. As long as P is greater than 490, which it is if it's 500, then this force will have a constant value of 490. Now in part 3 we want to find the acceleration if in fact 6 dogs are used. So if 6 dogs are used, then the pulling force will be 600 newtons. So we've increased P now from 500 to 600, but of course F always remains at 490 newtons. Now let's consider the resulting force on the sleigh. I will call the resultant force capital F, as I normally do. So we want to vector sum of these 4 forces. Now I'll just write it all down. Of course you don't have to write this down, but I just want to make it clear what's going on. So I'll just write down a vector equation here. And we can apply Newton's second law. So by Newton's second law, the resultant force is the mass times the acceleration. Well, the mass of the sleigh and its occupants is 500. And we multiply that by the acceleration. So we're just applying F equals ma. Now the vector sum of n and w is 0. So we don't have to worry about vertical directions. They always cancel out, because the sleigh will always have its acceleration in the horizontal direction only. The vertical component is 0. So we're only interested in the vector sum of f and p. So if we take directions to the right as being positive, we're just dealing with vectors in one dimension now, the horizontal direction. So the sign of the vector will give the direction. So the sign of f will be minus, because vector f is pointing to the left. I only have the magnitude of it here, which is always positive, of course, but the sign, minus sign, indicates the direction as well as the magnitude. And then we have to add on vector p. Well, vector p is pointing to the right, so that's positive. So we could put a plus sign to emphasize the direction. But anyway, so the resultant force is got by calculating this. This is 110 newtons. And as I've said already, that's equal to mass times the acceleration, 500 times a. So we just divide across by 500 to get the acceleration. So here's the answer. 110 divided by 500 is 11 over 50 meters per second squared. And that's positive, of course, in the same direction as the resultant force. So the resultant force is pointing in this direction. So its magnitude is 110 newtons. And of course the acceleration by Newton's second law is pointing in the same direction. And its magnitude is 11 over 50. So we could show the acceleration in blue here.